Hey guys, welcome back to Digital Srini channel on YouTube. And in the last couple of videos, we looked at how we can use global pooling layers to localize features in our images. In fact, a couple of videos ago, we looked at how we can do anomaly detection and also localize the features within these anomaly images. Now, if outliers or anomalies or outliers in general are important to you, whether it is in images or in time series or in other types of data, then there is a great library that I think you should explore. It's called Alibi Detect. I'm going to show that to you, of course, in this video, but I'm going to focus on images for now, image outliers in this video, but it can do a lot more, Alibi Detect. So first, let me quickly explain what Alibi Detect is, and then I'll jump into the code to show you an example on how you can use Alibi Detect to put together a outlier detector that can detect outliers in your images. And again, as we do for anomaly detection, the principle is very straightforward here, in this example at least, which is you train this on a whole bunch of good images or non-anomaly images, normal images, and then whatever is an outlier is an outlier. And of course, you set a threshold, and I said whatever is an outlier because when it comes to autoencoders, of course, you look at the reconstruction error and so on. So let me jump into the Alibi Detect a couple of pages so I can explain that, and then let's jump into the code without wasting any time. First of all, starting with their GitHub page, and I'll leave the links as part of the description. Also, I included the links as part of my Python file that I am going to share with you. So if you look here, you can see that the GitHub page itself has a lot of information. They have the code and all that, so you can go ahead and read it. Now, if you go down, you can see how you can install this, pip install Alibi Detect, and I did exactly the same and it worked fine. And what else can it do? Instead of looking at this GitHub page, let's actually click on the documentation page, which takes you to this amazing documentation. I can tell how good a library is just by looking at the documentation. If they cared enough to give us this type of help, then I'm pretty sure they have put enough energy, enough effort into coming up with great code that we can rely on. Okay, so first of all, what is this? It's an open source Python library, and they focused on outlier, adversarial, and drift detection. So if any of these is an interest, then you're at the right place. Then they have both TensorFlow and PyTorch backends for the drift detector. I'm not sure if they have PyTorch for the outlier, but they specifically mentioned that they have these two for drift detection. So definitely works with TensorFlow backend, which I'm going to use in the next few minutes. Okay, and what else do they have? I mean, they have many. You can spend like all day trying to learn exactly what they have. So they have this Mahalanobis distance-based outlier detection. This is something I've used literally almost 15 years ago or something, and then that name sounds so familiar. Isolation forest is another approach. I am going to show you variational auto-encoder approach, which is again very simple. You don't have to put together a lot of code, but you do have to put together some code, and they gave many examples, so you can copy their example and then go ahead and build on top of it. And autoencoders, and they also have VAEs with GMM, like Gaussian mixture models and so on. And they also have some drift detection. I'd like to test some of these, especially if they have like image based. And I should admit, I literally found this a few days ago, and I put together the code I'm going to show you, which means it actually worked very well without a lot of effort. So that's great. And you can also go through their amazing examples. They have an example for outlier detection on CFAR10 datasets and so on. And again, I'm going to show you on a different data set for this video. And I am planning on actually recording a couple of videos, maybe time series outlier detection. Again, I don't want to repeat everything that they have here, but at least a couple of these on just to make sure someone is there to explain you a couple of these applications. Okay, with that knowledge, let's go ahead and jump into the code. And first of all, Like I said, we are going to use this VAE outlier approach, like variational auto-encoder approach when it comes to outlier detection. I'm pretty sure most of you know what variational auto-encoder is. I have done a video on that. But when it comes to outlier detection, the best paper here is this. I think they have they model their VAE approach based on this specific paper, auto-encoding variational Bayes. Okay, so if you're interested in the math behind it or the theory behind it, go ahead and read this paper. Also, when it comes to dataset, a couple more things before jumping into code. I am going to use dataset that is based on this paper. Again, amazing set of data sets if you are interested in working with outlier or anomaly detection type of examples. If you don't have your own data, this can be a pretty good place. So how do you get your hands on this? Again, I'll share the direct link for this anomaly detection. So go ahead and to this guy's website. And you can see the examples that they have is the one I'm going to use is this carpet. You have a clean one, you have some anomalies, and you can see how when you zoom in, there is an anomaly right there. And hopefully we can classify these images as outliers and these as good ones. And we're going to use these as good ones for our example. They have many other, I think you see bottle, I don't know how the images look like. And if you want, you can download all those. It's about slightly less than 5 gigabytes. So I downloaded the carpet dataset right there. And when you open it, it should look something like this. They have a ground truth, they have train and test. I'm just going to use only the train images for now, and they have good and 280 of these good images. So I'm going to use these 280 to train the model. And to validate that, of course, I'm going to use some of the images over there, and they have some bad images. Not all are obviously bad, like some you can't even tell. Like if you look at this image, let's see how our outlier algorithm performs. And again, like any other outlier or anomaly detector, you have to set a threshold. And this library, Alibi Detect, actually gives us very nice tools to find out what an appropriate threshold would be. So with that information, let's jump into the code. Okay, so again, as usual, I have written a lot of text here and a few links that I think will be useful for you. So go ahead and look at this at your own pace. So let's jump in. So first of all, I'm going to import OS, OpenCV, Pillow, NumPy, Matplotlib. No surprise there, right? So everything that we need to read the files from the directory or handle images. Okay, then I'm going to import TensorFlow in case you're curious what version TensorFlow I'm using. It's 2.4.1. Okay, and from TensorFlow.layers, I'm going to import con2d transpose, dense, and everything. Why? Because to use this, you have to define some sort of your own autoencoder, an encoder and a decoder. It can be anything, an encoder and a decoder. I'll show you what I have, just 3 layers in each. That's fine. So to do that, you need, of course, a way to build that. So I'm using Keras. So let's go ahead and do that. Now, by the way, installation is easy. Pip install Alibi Detect, like I mentioned. So it worked pretty fine for me. I didn't have to jump through any hoops to get it running. So it worked fine. Okay, now let me separate this from my Alibi Detect.od. Alibi Detect is their main library. OD is outlier detector, apparently. .od. I'm going to import outlier VAE. In fact, you can use AE if you want, autoencoder. I'm using variational autoencoder right there in this exercise. So let's go ahead and import outlier VAE. And also from the utilities.visualize, let's go ahead and import plot so we can easily plot a couple of things, and also plot figures, because once I have the outliers, I want to plot those and then just show the hotspots. So for that, I'm going to import those 2 methods. So let's go ahead and do that. And now let's come down to the part where we read these images. So I have those in my train folder, and I'm going to use the good images for training. So let's go ahead and read good and bad images, good for training and bad for just testing. So I create, and let's go ahead and read them at a size of 64. There you go. And I am using os.list there to look under my good. Let me make sure these are all PNG images. Look for PNG and go ahead and use OpenCV to read them. and I convert that image into a NumPy, into a pillow image. Why? Because it makes it easy for us to resize it to 64 by 64, convert it back to NumPy array. That's it. And then go ahead and capture all of these as a NumPy array dataset. Okay. And once I do that, let's go ahead and run these up to the dataset point. Okay. So now let's create some room there. My dataset has 280 images. Of course, that's how many images we have, each 64 by 64 by 3. So normally we split data into train and test. So let's go ahead and do that. So for the first 200 images, I'm assigning that to train. So I'm going to use 200 images for my training, and the remaining 80 images, I'm going to use those as, or 79. I'm going to use them for testing purposes during my training process. So because these images are all unsigned integer 8s, let's go ahead and divide them by 255 to scale them between 0 to 1, both train and test. I'm doing exactly the same for my bad images or outliers. Remember, I'm not using outliers for training. I'm just loading them so I can use it later on during my testing process. So let's go ahead and do this, do the same. And here we only have 89 images, so let's go ahead and keep them. Now let's define our encoder. So the way, again, based on their example, I'm just following this based on the examples that they gave, slightly modified, by the way. And the encoder dimension is, remember, you have an auto-encoder, right? So you have a large size image which gradually goes down into a small vector and comes back up. And what is that vector size? What is that encoder dimensions? So here I am defining that as 1024, and also the dense dimension. Why do I need these two? So I can define my decoder. Okay, so for my encoder, I don't even need the, well, encoder dimension is what's needed, so I can go down to that. So first, let's go ahead and run these two lines, and I'll tell you what dense dimension is in a minute. And when I define the encoder, okay, it's pretty straightforward. I'm using the sequential method in Keras, and I'm defining conv2d layer with 64, 128, and 512 filters. And I'm doing, again, 4x4 kernels. You can do 3x3 and try, and strides equal to 2 in this case. And I'm going to use ReLU activation right here. And the end of this is going to be a encoded vector of size 1024. So if I go ahead and print my encoder summary, you should see that 32, 32, 64, right? I mean, we're going from 64, 64, 3 to 32, 64, 128, 512, and then this. And finally, the dense layer, the output, it has 1024. That's exactly why I'm defining that there. Also, if you look at this conv2d, the final convolution 2d, 8 by 8 by 512. That's exactly what I'm defining here. Why? Because in our decoder, we want to follow symmetrically opposite path. So we'll start with that many dense layers, and then we'll work our way back. That's exactly why we need that. Okay, so now when you look at the decoder, you know exactly what we're trying to do, right? Our input layer has a dimension of 1024. That's where we start, because the output of this is the input of decoder. So that's what our decoder is. And then we go into dense dimension, you see, 8 by 8 by 512. So let's go ahead and multiply 8 by 8 by 512, which is nothing but 32,768. So that's what we have right there. And then we reshape that to 8 by 8 by 512, and then everything follows symmetrically. So let us go ahead and print this, and hopefully you'll see that this is symmetrically opposite to before, right? So 32,768. 32,768, 88,512, 88,512, and we just work our way back up all the way to our original image size of 64 by 64 by 3. So we just defined our encoder and decoder. Now let's go ahead and define our outlier detector. So how do we do that? So first of all, our latent dimension, what is the dimension right there, the central 1024, right? So let's go ahead and define that with a different name. I could have used basically the same name, encoding dimension, but let's go ahead and define it again. And our outlier detector, again, go ahead and look at the documentation for more details. But in this case, we are using outlier VAE. You can use outlier AE. You can use outlier, what else do they have? It's important. Let's go back. You can use outlier. In fact, if I go here, so let's come down. So for outlier detection, this is what they have. So for images, you have autoencoder VAE, autoencoder Gaussian mixture model, VAE Gaussian mixture model, and likelihood ratios. These are all the ones that you can use for For images, I personally like VAE because I know what that is. And also because in this case, if I want to print out the feature level information, VAE gives me that information. So this is why I'm sticking with either a VAE or autoencoder approach when it comes to image anomaly. When it comes to tabular data, you have a few more options right there. So go ahead and look at these to make a decision in terms of what's appropriate for you. So based on that, I picked VAE, outlier VAE, and also we need to provide a threshold value, because think of this as your reconstruction error threshold, above which you call these outliers, and below which you call them acceptable, non-outliers. How do you know what the threshold value is? You just start with something that makes sense. I'll show you how we'll update this after the training process, but let's start with something, 0.01, 0.015, whatever, based on my previous experience. I just leave this value right here. And score type, use mean squared error reconstruction error for outlier detection. That works great. And what is my encoder network? Encoder network is what I just defined up here. That's my encoder. The decoder is right here, decoder. Okay, and my latent dimension is 1024, right? That's my latent dimension. And samples, I have to go back. Sorry about that. Samples equals to 4. I don't want to look at the documentation right now, but I think this is something similar to batch size. Again, look at the documentation for that. I meant to put a comment right here. Again, I apologize for that. So let's go ahead and define our outlier detector. This is just defining it, right? This is like defining a model. Now we have to do model.fit. Okay, so think of this as a model. Outlier detector is putting together a model for you based on your encoder and decoder, and then we have to do model.fit later on. So first, let's go ahead and define this. So let's run these lines, and once that's done, let's print the current threshold value. If I can type the correct spelling, yeah. So the current threshold value is 0.015. There is a reason why I'm printing that, because I want to show you how to update and then show you that it actually got updated. Anytime you have a question, your model, I call the model OD, you can call it anything, my model.threshold. This gives you the current threshold value. Okay, now let's go ahead and fit the model. How do we do that? First of all, you define your optimizer. In this case, I chose to use Atom. And by the way, they also have like different losses on their library. Under their library, like there's a loss for evidence lower bound loss, like elbow loss. I was experimenting with this, but again, there are a lot to experiment. If you really are into this field, I'm just giving you an overview of this library so you can explore it further. Let's go ahead and fit this for 20 epochs. Let's not waste your time or my time a lot here, but I think 20 epochs is okay. Batch size equals to 4. Optimizer is Atom. Verbose is true, so we can see something on the screen. So let us go ahead and run this and see once it gets started. And then let's also print out, once it's done, the current threshold, just to show you that training will not update the threshold. You have to do that manually. So there you go. So it's 1 epoch almost done right there. So as you can see, this takes a few more seconds. So let me go ahead and pause this video and continue right away. So stay put. Okay, there you go. It's done a few minutes later. So let's go ahead and check the current threshold. It should be 0.015 because we did nothing. I mean, we haven't updated the threshold. So first of all, let's go ahead and do that. Yeah. How do you do that? First of all, how do you know what the right threshold is? So there is something called Infer Threshold as part of their library. And you take your model, like OD in our case, right? That's the model name, .infer threshold. So it kind of gives us a good idea of what a good value for threshold would be. And for that, let's go ahead and use our test data. What is our test? Test is my 79 images, each 64 by 64 by 3. And I'm going to say outlier type is instance and with a threshold percentage of 99. What does that mean? Well, instances are considered to be outliers in a sample of the data set. So go ahead and look at the instance and the percentage of our images that are considered to be normal based on the outlier score. So basically I'm saying that, hey, in my input images, like 79 images, I think about 99% are normal images and 1%, I'm just setting that. I know all 100 images are normal images. but I'm providing normal images and saying that consider that 99% of them are normal and 1% are not normal. So what threshold would you recommend? That's exactly what that is. So when I do that, od.infer threshold, whenever you do od.infer threshold, it automatically updates the threshold value. So when I print the od.threshold, you see it's giving me a value of 0.0033. So you don't have to manually update the threshold anymore. It automatically did that for you. So from now on, the threshold is 0.00333, whatever that value is. You can change that. If you want, you can just say, hey, I don't like that. I want to keep it something else, provided you have some information about what that value should be, which we'll gain in a minute. Okay, now, as usual, you can go ahead and save this model and also load the model. But on their website, they specifically say that save and load is having issues in Python 3.6, but they work in Python 3.7. And I can confirm that in Python 3.6, which is what I'm working on, these things do not seem to work fine, meaning I can import the library, but when I say save, it says it throws some error. Let's not get into that. Test our model on a bad image. Well, if you want to get into that, I said let's not get into that, but if you guys run into that issue, then what would you do? So let's go ahead and import this, both save detector. Yeah, that's the problem. I don't think I can even import those. It says cannot import name save detector from alibi net.utils. And I think I'm working in Python 3.7, so I'm not sure why they have that issue. Again, I haven't completely looked into troubleshooting any of these yet, but let's move on to testing our model on a bad image. So how do we test this on a bad image? Well, first let's go ahead and load a random image. Let's leave it to 9. That's okay. I was about to change it to something else. And get it from our bad dataset. Remember, we loaded the bad dataset. So let's go ahead and load an image from bad dataset. If you want, go ahead and look at it. So here is how the image looks. There's a fine line right there. That is the defect in this image. And let's hope it picks that up and labels this as a outlier and not an inlier, right? So let's go ahead and reconstruct our bad image just so we see how the reconstructed image looks like, right? So it's od.vae on this image. So we are using variational auto-encoder. So it's reconstructed. Let's go ahead and, by the way, when you reconstruct an image, it's actually a tensor object. Image bad image recon, test bad image recon. Yeah, that's a tensor object. Let's convert that to NumPy object right there, and then plot it. So there you go, very nice and clean, and this is the input image. So it will look at the difference here and says that, hey, there is some additional, extra error right there. That's the hope. So now let's look at the instance score. Okay, so when you take your test bad image predict, which is my od.predict. In fact, I haven't done that. So let's go ahead and predict. So far, we reconstructed the image. We haven't predicted. We need to predict by saying, okay, is this a good image or a bad image, right? So let's go ahead and predict on my test bad image. Again, my test bad image has the same dimensions as you normally would expect. Number of images, height, width, and number of channels. So let's go ahead and predict it. And when you do that, when you look at the prediction, it's a dictionary of 2 entries. The first one, data, the second one, meta. Under data, you have feature score, instance score, and is this an outlier or not? I can immediately see that it's saying it's not an outlier, 0. 1 is an outlier. So my threshold value is not good enough. We'll check that later. Instance score is 0.0022. What is our threshold that it recommended? We'll check that in a second. But instance score is basically what it is looking for in terms of threshold, and then saying if this is an outlier or not. So I'm just printing 0.0033, right, is our threshold. Anything above that is an outlier, below it's not an outlier. Obviously 0.0022 is below, so it says, hey, it's not an outlier. So we have to play with this setting in a minute. Okay, and feature score, this is basically your feature map. At every pixel, it's giving you the score of it being an outlier. This is a great way of visualizing where the issues are in your image and why is that considered to be an outlier. So let's go ahead, close that, close this, and get those values from the dictionary. And how would you do that? How would you get these values from a dictionary? So we have our test bad image predict, right? This is the one with dictionary. Within the dictionary, let's look at the values for the keyword data. Within that, let's go ahead and look at the instance score and go ahead and print out the instance score. We know that it's 0.0022 something. Same thing, let's do that for our feature score. Feature score is this feature image. So let's go ahead and plot our feature score image so you can visualize exactly where the issue. That's not bad. I'm impressed. You see that area where it is actually showing these, except it's not strong enough. So it thinks that it's not an outlier based on our threshold. Okay, is this an image outlier or no? Obviously, the answer is it's not an outlier. So what if I want to change the threshold to 0.002? Because this one has 0.0022 and I want to include this as part of my outlier. So this is exactly the exercise that you have to do in an iterative way to figure out exactly what an outlier is in your images. So let's go ahead, and how do you set a threshold? It's basically od.threshold. Remember, print od.threshold is giving you what the current value is. Like when I run that, it just says it's 0.0033. Now when I do equals to 0.002, it sets the threshold to 0.002. Now let's print the current threshold value is. It's whatever we defined. Now let's go back to this question. Is this image an outlier or not? Oh, we have to bad instance score right there. Oops. Let's run these ones. Oh, it still says 0. Let's check. Let's actually check this on multiple images. Okay. So unless I did a mistake in terms of our threshold, this doesn't make sense. But let's go ahead and apply this on multiple images so we can see how the spread of these threshold is. So here, what I'm doing is from the bad data set, I'm getting 20 images. Okay, right there. So my X is 20 images, and let's go ahead and do predict on my X. Outlier type is instance and return feature square. Yes, we want feature score and we want instance score so we can plot both features and also look at the instances. So let's go ahead and do that. Okay, I'm just printing this. I should have commented that out so you can see that, okay, we have instance score, feature square, and is this an outlier or not? Based on that, we can go ahead and plan our plotting. So first thing first, let's go ahead and scatter plot these labels, these instances. How do we do that? First of all, let's go ahead and define our target as all ones. Yeah, my target is all 20 as ones. Why? Because I know all of these are anomaly images. So I just want to set that as my target. And my labels are normal and outlier. And I'm defining this so I can use this plot instance score, which requires the predictions, what the target is, what the labels are, and what the current threshold is. It just puts a straight line at the threshold. So let's go ahead and look at the plot, and there you go. So the current threshold is right here, and apparently all these images, all these 20 images are outliers. Of course, we know that because they're all outliers, in this case, bad images. So a threshold of 0.002 seems to be a pretty good threshold. I don't know why that other image did not work. Maybe I should go back and recalculate and see if there is an issue somewhere. But as you can see, all these 20 images are above my line right there. So we got the threshold right in this case. So let's go ahead and plot some of these images. So let's plot both the, when you use the plot feature outlier image, remember these are the two libraries we imported from this, two methods, plot instance score and plot feature outlier. So plot feature outlier requires your predictions, which we just did up here, and your input data and your reconstructed images, because it's just plotting all of these side by side. And how many images, like instances, would you like to plot? And if you provide instant IDs, it's going to plot those specific images, like 0th image, 5th image, and so on. Okay, let's go ahead and run this so we can have a nice look at the final result. There you go. And this is the final result. And here are the 5 images. And they're all, of course, labeled as outliers. And you can see why they're outlier, because in 0th channel, 1st and 2nd channel, there you go. That's the information. And you can see how in 0th and 1st, in the second channel, not much going on at that spot, but now we have localized our anomaly right there. So this is just tip of the iceberg when it comes to what this library can do, and I hope you guys really appreciated this specific library right there and the type of work they did. And more importantly, I believe they even have like amazing if you don't want to go through this help, if you just want like to download a PDF, they have everything in a PDF format right there, which is very easy to read and underline if you're like me. There you go. So this is all in a PDF format, so you can go ahead and get a good understanding of exactly what the strengths of this library are. So okay, I really hope you learned something new here, especially if you are interested in outlier detector. Like I said, I'll probably pick a couple more examples and make some videos in terms of how to implement, because oftentimes you read this and you know that, oh yeah, you define an encoder net, you define a decoder net and all that stuff, but how do you implement on your images, right? So that's why I try to make a few videos using my own data, so you get a better understanding of exactly how the implementation goes along. So thank you guys again, and I request you to subscribe to this channel and like this video if you really happen to like this type of content. Thank you.